So I can't do that because they don't have the same base. Do you agree?
What?
Oh, I didn't get that.
Oh, yeah.
That's what
They don't have the same base because, yeah, you can put that in your calculator, but will you have a calculator on this quiz? Nope.
No?
When do we?
So we were supposed to do the homework without a calculator?
Should be able to do all this without a calculator. What I want to do here is I want you to start to pick up on these subtle nuances of the bases. 4 and 64, they're both what?
Multiple 4.
Perfect squares, and they're both evens, aren't they? Okay? Here's what I'm going to do. How do I rewrite 4 with a base of 2?
8
squared.
over 2.
Means the same thing, right?
Yeah.
You okay with that? 64. Well, let's see if we can get that to work. 64. Excuse me. Does it work with 2's?
Yes.
See. 2 squared is 4. 2 cubed is 8. 2, and then 2 to the 4th is 16. 2 to the 5th is 32. 2 to the 6th is
64.
Now I have power to power on both of those, don't I? The answer is yes. Okay, very good. What's 2 times a 4th?
What happened?
Good. What's 6 times a 4th?
Darn.
And change.
6.
3 over 2.
What are you guys talking about?
How did you get there at all?
How'd you get more?
What's 2 times a 4th? It's 2 over 4. What's 2 over 4? 1/2. What's 6 times a 4th? 6 over 4. What's 6 over 4 simplify to be? 3/2. Do those have the same base?
Yeah.
Do they have different exponents?
Yeah.
What do
Yeah.
you do?
You add them.
What's 1/2 plus 3/2?
2.
4/2, otherwise known as?
Oh, that's easy. I didn't get that.
Oh, I got
You break it down to the simplistic base, and you build yourself out. Here.
So I put it in like attic with like 4 and it's 4 underneath.
The 4th root, yeah.
Yeah, and then 4 underneath, like 6. I don't know what the
The 4th, the nth root. So you did the
Yeah.
nth root, you multiplied
yeah,
the.
and then you multiply 4 and 64, and then.
Then look for your perfect
Yeah.
4th. Yeah, you can do that too. I always find. I always find that it's easier to break it into bases because the exponent rules work. Strict sleep keeps getting it. Exponent rules tend to work a little bit quicker because if you don't know perfect 4th roots, it's tough. You know what I mean? I mean, you get there, but it's a little bit tougher that way. This way, it breaks it down to something a little bit easier to work on.
Yeah, but if you
Okay.
don't know like what 2 to the power is 64.
It's one of those things you're gonna have to learn. You have to start looking at it. That's why I said the subtle nuances of this stuff you have to pick up on. Okay? You go to that 27, same basic idea. I have different bases, but I have the same exponent. Okay? I need to try and get them into the same base. So when I'm looking at it, I have 70 to the 3rd and 14 to the 3rd. I don't know if I would be able to get that to a base, though, am I? Because 70 is just 7 times 10. 14 is 7 times 2. So let's do this. Can I rewrite this?
Yeah.
Is that okay?
Yeah.
All right. Now, we just said that 70 was 7 times 2 times 5. You okay with that?
Yeah.
14 is 7 times 2.
Cancel out.
So what is, if we break it down in terms of primes, you have 7, 2, and a 5 over 7 and a 2. Am I okay with that?
Yeah.
This is all to the 3rd power, right? What's your answer?
5.
5 to the
1/3.
5 to the 1/3.
That's cool.
Now, the general idea here is, I'll get you one second, Hope. The general idea here is if you start with an exponent, you can leave it as an exponent. If you start with an nth root, you leave it as an nth root. Yes, ma'am? I did. Some people might not pick up on that it's 5 right away. That's all I'm saying. If you picked up on it, cool, go for it. The only reason why I'm saying is that I'm simplifying this out, and if this was, some other value, I'm just showing a way that things simplify out. What you did is perfectly fine. Okay. All right. Let's see, what's the other funky one? If you look at 30. This is that same idea where you notice how they all have the same exponent, but yet there's nothing I can do right there with bases. I can't write it down like we do with that 2, or it's 2 to the second and 2 to the 6th or anything like that. So since these guys all have the exact same base, I can kind of do the same thing we just did with that 70 and the 14. Simplify the fraction prior. 6, 4, 3, all of the 2/3. What do you get? 8 to the 2/3. You get 8 to the 2/3. Are we okay with that? This simplifies out to become 4 times 2, so you get 8 to the 2/3. Now, that means what is the cube root of 8 squared? 4.
41.
I'm getting there. Like I said, I'm going to slowly build out of this. Those are cool shoes.
Wait, yeah, where did that? It's because 6 over 3 is 2. Yeah, but
So
you
just
can't
leave it
follow
as that.
6.
Oh, so he wrote the values and then he wrote that after. Okay, got it.
If you leave it as that,
Oh, I'm sorry. We said the answer out loud. The cube root of 8 was 2. 2 squared was 4. You always try to simplify out as far as you can go. Okay? You always try to simplify out as far as you can go. All right? I'm using these properties of the power to power of the distributive property of the exponent. If I can take the stuff out, write it as one big fraction since they all have the same exponent, simplify the fraction, and then put it back together. Just working back and forth. Let's see, the rest of that one. Now when you get into, excuse me, you start getting into the next grouping, some of these guys right off the bat, you can't multiply them together right away. To be honest with you, when I see radicals, nth roots if you will, I like to rewrite them as their base with the fractional exponent. I always think that it's easier to do all of the junk with this when I have a fractional exponent. I think it's cleaner. So if I'm looking at 64, the square root of 64, I know that is 64 to the half power. We okay with that?
Yeah.
All right. Then it's 64 to the third power. Are those the same base?
Yeah, wait.
64 is the base, and the exponent's a half and a third, right? So if you have the same base, different exponents, and you're multiplying, what do you do to the exponents? You add them. So I'm going to add these together. I get 64. This becomes 3/6. This becomes 2/6. So that is?
1/2. Oh. Oh.
Okay. Now, remember, that means what is the 6th root of 64 to the 5th power?
32.
Very good.
Why can't you just like find the square root of 64 then?
Yeah.
You do that too.
You can do that too. I'm showing how, because when it gets to some of the more complicated ones, it's easier to go that route.
Oh, okay.
And there's nothing wrong with that. Absolutely nothing wrong. What they're doing here is, you know, this is 8, and that was 4. You get the same thing.
That's what I did.
It's fine. But as we,
I used my calculator,
because when we start to mix these up, I'm just trying to show you guys, the more you get comfortable by using some of the fractional ones, it's going to be all right. Okay? Same thing here. 8, the fourth root of 8 and the fourth root of 2. This is the same thing as saying, 8 to the fourth, 2 to the fourth, but I can't do anything there, can I? There's nothing I can do because they don't have the same base. So what I need to do is I need to rewrite that as a base 2. How do you do that?
2 to the third.
Good.
To the 1/4.
So 2, excuse me, this is 2 to the third to the fourth. We okay with that? What's the next step to write that as? Which you get then what? Good. So now I have 2 to the 3/4 times 2 to the 1/4. Same base, different exponents as you're multiplying, you add them together. What's 3/4 and a fourth? 1. Otherwise known as 1, so your answer is?
2, 4.
I don't know why you can't just multiply 8 and 2 and 16
That is fine. All I'm doing is showing, I'm trying to get you guys the idea that switching bases to the rudimental base is okay. Because I'm prepping you for the hard stuff in logs.
But I have a question.
Same base, different exponent, you add. Same base, different exponent, we add. So 3/4 and 1/4. Yes. When you had this, x cubed times x to the fourth, what'd you do? What's 3 plus 4? 3 plus 4.
Oh, I just thought X.
Oh, yeah, it's this one. I'm sorry.
I thought X to
Yeah, you're adding exponents.
Yeah.
Same idea. Yes, ma'am.
In the second one, why can't you just multiply 8 and 2 together and then divide them?
I just said that 30 seconds ago. I'm preparing you for logarithms. Yes, ma'am. Well, I'm getting there. Okay, I'm getting there.
Just need a spreadsheet.
If we're in dollars. We might.
38. In 38, you have the same base, but different nth roots. Are you okay with that?
Wait, what question is it?
It's 38.
I'm sorry,
Okay, Phoebe.
All right, Phoebe, I want to make sure you're listening. You ready? Okay, what's bigger, a half or a fifth?
a hat.
Okay. I thought about it for a second, I know, and I appreciate it. So who would win in the battle of war, half or a fifth? All right, so that means you have same base, different exponents, means you're going to subtract them now. So it's 7 to the 1/2 minus 1/5.
Oh.
That's not a terrible fraction. Yes, ma'am?
What if the bottom is bigger than the top? Where are those?
We'll get there. Because then you have to worry about rationalizing them. And we're not there yet. Just relax. No, you'll have to.
So maybe it won't happen right now.
Well, not in this problem, because 1/2 minus 1/5, well, that's 5 over 10 and 2 over 10. So you get 7 to the 3/10. And you're done.
Oh my god.
Get that.
Just leave it.
I'm going to have you guys leave them in terms of positive, rational exponents. Perfectly fine, okay? But look how the problem presented it to us. It presented it in terms of nth roots. So what should I finish this out as?
That 10 root 7 square cube.
Something like that. Remember, it's math etiquette to finish your result with how it started. Okay? Is it starting to become less fuzzy?
A little bit, not really, but I mean, it doesn't really mean much to me.
You mean much to me, though. And I want to make sure. I have my moments of being nice. They're far Oh, that's Mr. Sour. Now,
Solomon's just rude to us.
in this case here, you guys have, most of you guys have been looking at it saying, hey, I've got the same nth root, which means I can just combine all of my fractions there, the 8, 16, and the 2. That's what most of you guys have been thinking, right?
Yeah.
Okay. You get what, the 6th root of 64? What is it? 2. You can do that. And now, Emma, the reason that I'm showing you the long way.
What do you want there?
No.
Just combine it.
That's fine. Once again, guys, the reason to which I'm showing you the long way here is I'm preparing you for working and dealing with logarithms. Logarithms, bless you. Besides being allergic to logarithms, you will find out that they deal with bases and exponents. And in order to do anything with a logarithm, you have to have the same base. I'm just preparing you to show you how you can convert bases. Sir.
When is this logarithm you speak of?
That's probably after break. Yes, ma'am.
Where did you get the 64?
I simplified the roots here. What's half of 16?
8.
What's 8 times 8? See what I'm getting? All I did there is, since these guys all have that same 6th root, I wrote it as 8. I can do that. Okay. Now, in the other one, I can't do that with the whole fraction though. Yes, ma'am.
So this is just a general question. Wouldn't something times something divided by something? If it's like divided by 2, you can just one of the pieces that you're multiplying divided by 2, and it's considering this one instead of divided by 1.
What's 3 times 4 divided by 2?
6.
Okay. What's 3 times 4?
12.
12.
Divided by 6. Or divided by 2.
6.
Same thing. Just, you get the same thing.
So you can do that?
Because
so
the order in which
you
you...
8 by 2 and it was 4 times 16 and 16.
Because the order in which you multiply doesn't matter, because isn't dividing by 2 the same thing as multiplying by?
Negative 1/2?
Not negative 1/2, just 1/2. It's just orders, that's all it is. Now this one, there's a couple of ways of going about it. There's a couple of ways to set this one up. Combine your nth roots at the numerator, combine your nth roots in the denominator, and you get the 3rd cube root of 54 over the 6th root of 4. You okay with that? I hope.
I don't even know what I'm doing.
Now, at this point, I need to try to figure out how can I get these two values to have the same base. This is where I look at the fact that they're even. Last time I checked, 4 and 54 are both even, right? So I know I can rewrite the 4 as a base 2 by saying it's 2 squared. You okay with that? 54, well, can I simplify that cube root?
Yeah.
Yeah.
What do you get?
3 root, just cube root 3.
Okay. You get, this is 27 times 2. Do everybody agree with me on that?
Yeah.
So can I just write it as 3 cube root of 2
Oh,
over the 6th root of 2 squared? Is that okay?
Yeah.
yes.
I rewrote it as base 2. This was 27 times 2. Cube root of 27 is 3. Now, I'm going to change these nth roots to fractions because it's easier to work with. When I do that, I get, I'm going to bring this over here, 3 times 2 to the 1/3 over 2 to the 2 times the 1/6, which happens to be what? What's 2 times 1/6?
2 times 1/6 is 1/3.
What's 2 to the 1/3 divided by 2 to the 1/3?
1.
Bless you.
Oh my god. I did not do that. Like, I started to do the first part.
Jeez, how am I supposed to read that?
I was not able to use the calculator.
I'm sorry.
Oh, you simplified it here. 6 root 2. You did that 2 squared with the 6, so you simplified it right off the bat. It's the same thing I did for the 6. Alright, once again here, what I'm trying to do is I'm trying to find how can I rewrite things in terms of having the same base. God bless you. When we do that, you might find out where you get pleasantly surprised. You get something that's 2 times 1/6, which is 1/3. That's why 2 to the 3rd divided by 2 to the 3rd simplifies out. Okay? You divide out and you get 1. Cube root 2 divided by cube root 2 is just 1. Yes, ma'am?
So when you're crossing out those two 2's right there, did you cross out the square or did you leave it?
Yeah, because when
Because like it's not the same, so you're thinking it, right?
remember, what this is, I have 3 times 2 to the 3rd over 2 squared to the 6th. What I did here was, this simplifies is 2 to the 2/6, which is 2 to the 1/3. So this divided by this is 1. I just spoke through it. Okay? Here.
Okay, so you know when you had it in like non-fractional exponent before, did you put 2/6 for the fractional exponent and then that was simplified to 1/3?
Yes. Yeah, because you have 2 to the 1/6 times 2 to the 1/6, you get 1/3 right off the bat. That's fine. I think that's what you did. Yeah, that's fine. Remember, what I'm doing here is I'm showing the long form of it just to make sure that I'm not cutting any corners on a lot of this stuff, just so to catch one, but that's fine. Where we leave off here?
47.
Let's start with this. And this is where rationalizing comes into play. Okay? And when I went back and looked at how I was doing I did that rationalizing with you guys, I brain farted and I was dealing with a square root as opposed to nth root. So let me show you something here real fast. Do you want radicals in the denominator? No, you want them to become, you want their exponents to be a power of 1, correct?
Yeah.
All right. Now, I'm going to rewrite this as 1 to the 3rd over 7 to the 3rd. You okay with that?
Yes.
All right. Now, I need to create that 7 to have an exponent of 1, which means I have to add to the 3rd how much?
2/3.
So we have to multiply top and bottom by.
2/3.
That's how you rationalize rational exponents.
I'm so happy that we did that already. Oh my gosh.
I can't believe
It's a good thing Mr. Tate stopped by, right?
Yeah.
I know. I know.
I did this by myself.
And that's how that works out. So,
Wait, what did he teach?
he's got pre-calc and algebra B this year, but yeah, he's.
So we can have
I thought his
You can have
name
next
was
year.
Wait, why?
You want to create. Excuse me again. You want to create the exponent of 1.
Oh, okay.
Okay. So what you're doing is how do you make that 1/3 into a whole? You add 2/3 to it. It's that easy. If you think about when you did that with square roots, it was 1/2 power. You multiply it by another 1/2 power.
Would that end up being 7/7 would be
Wait.
Well, no. This here is the factor of 1. So this becomes.
Oh, yeah.
What's the cube root of 1?
1.
1. So this becomes 7 to the 2/3 over 7.
Okay.
That, because the exponents add together, 1/3, 2/3 is 1.
Okay.
Now, that's 7 to the 2/3, since I was started as an nth root, I just need to rewrite that as an nth root. So it becomes the cube root of 7, squared all over 7. And then there's nothing left to do.
Why is it 7 and 2/3 and that's 7?
Squared.
Here?
On the top.
On the top. Because if I divide that out, what do you get?
1.
That's why.
Okay.
Because I'm multiplying it by a factor of 1, which doesn't change it, it just changes its shape, if you will. Yes.
Then why is the top 7? I don't understand. Like, why do you have 7 times 7 is 7 and 7 times 1 is 7? Why are they both 7?
It's not 7 times 7 down here. This is 7 and 1/3 times 7 to the 2/3.
Yeah.
Same base, different exponents, you add them. What's 1/3 plus 2/3?
3/3.
Right.
Okay, well then why did you do 1 at the top?
Because of that 1/3 plus 2/3.
They're not the same.
These are two different things. This cube root of 1 is 1, so that's why it just kind of went away. Let me do another one here. What do you got?
Are you trying to make it 1 or any like whole number?
I'm trying to make it 1. I want the exponent down here to be 1.
So if you had like one of those like 6/5,
Then,
What if you can't make it?
then you would have simplified something differently. That's a rare.
I'm just saying like for an example.
Yeah.
Like a bigger number on the top than on the bottom.
You can take a factor of it out. Show you another one. I think, is that one clean?
47.
2/3 and like this is so hot. So
47. So we're going to rewrite it again. I know that 81 can be rewritten with an exponent. It's 3 to what power?
3 to the 3rd power. 4 to the 4th.
81 is 3 to the 4th power because it's 9 times 9, which is 3 times 3. Okay? So in the denominator here, I get 2 times the 6th root of 3 to the 4th. Everybody's, yes, ma'am?
Can you write it as like 6, like 3/4, and then like the 4 on like on the inside?
It's supposed to be on the outside technically.
And you do the same thing.
I'm not going to yell at you. It's semantics, really. I'm trying to keep following the pattern of the end of the. So, does everybody see how this is going to how it's going to become 3 to the 4 6?
Yeah.
Yeah. Wait.
Oh, yeah, now I do.
So 1/3.
So it's 3 to the 2/3. That denominator becomes 3 to the 2/3.
I don't get that.
I simplified it out. I rewrote it as 81 to the 6th. 81 is 3 to the 4th, which got me here. All right? I simplified 4 6 and I get 2/3. What do I have to get to that to make it a whole? 1/3. So I have to multiply top and bottom by. Now, 3 to the 1/3 is cube root of 3. You agree? So my final answer becomes 2 cube root of 3 all over 3. It's not that bad once you start breaking into those exponents. When you rewrite it into the exponents, it's very easy to see how much more of the fraction you need to get to a whole. Okay? It's that straightforward. All right?
Where'd you get like 2 cube root to the 3? How did that all?
Here?
Yeah. Well, on the top and like the bottom, that be the answer.
Oh, 3 to the 1/3. 3 to the 1/3 is the cube root of 3. Okay? I started with an nth root. I got to finish in the nth root.
Oh, I got that.
Okay? So I just said that that's the cube root of 3, so I just rewrote it.
And then it's 2 times that. Okay.
Yes, sir. Okay. Same basic principle. I have a 4 and I have an 8. Does everybody agree that I can rewrite both of those as base 2?
Yes.
Okay. So if I rewrite both of those as base 2, the numerator, if it's the cube root of 4 squared, or excuse me, the cube root of 2 squared, how could you write that exponent-wise?
2 to the 2/3.
Good. So everybody is okay that that's 2 to the 2/3, right?
Yeah.
In the denominator, what would that be?
2 to the 3/5.
Very good. The denominator is 2 to the 3/5.
Because you have to get, it's 2 to the 3rd power to get to 8.
This is,
3 times 1/5 equals 3/5.
now, at this point, excuse me, since we have the same base with different exponents, we got to figure out who would win the game of war. 2/3 and 3/5 are ones that I know off the top of my head, but if I got a common denominator, what would that be?
15.
They both be 15. So just for argument's sake, this is, was it 10 to the 15, and this would be 9 to the 15th. So do I need to worry about rationalizing this denominator at all? No. What is my answer?
1 to the 15th.
Excellent. See how it's the same base, different exponents? You play the game of war. Who wins? It started out as an nth root, which means I have to rewrite it as an nth root. This is the 15th root of 2.
So how do you add to the roots?
Same way you'd add exponents, add the variables. You'd have to add them as long as they have the same base, same variable, same base, same exponent, you can add them. Okay? Yes, ma'am? Did I skip over it? Yeah.
the same base.
That exponent's not happy, is it? Where's it happy?
And or at the top.
Same base, different exponents, multiplying. What do you do?
Ooh, you add them.
13.
A lot easier, isn't it? I figured as soon as you saw me put it up, here you go. Now, as you get into rewriting them and combining them as far as adding, subtracting, and all that, your rules for adding and subtracting don't change when you're combining like terms. You have to have the same base with the same exponent in order to do that. Works the same with roots. So if I'm looking at 50, I'll just pull these two right off the bat. If I'm looking at just both these two, my root here, or I should say I have the fifth root of 6. 6 is the base, the nth root is 5. Same thing on the other one. Base is 6, nth root is 5. Can I combine those two?
Yes.
Okay, what's 1 plus 5?
6.
Your answer is 6 to the fifth root of 6. It goes the same way as you guys did in the past, where you'd have the square root of 3 plus 2 root 3. You'd get 3 root 3. It means the same thing. Your nth root there was just 2. Or it was the half power. It means the same stuff. It doesn't change. It just looks weird. Right? Same idea here. I have 160 to the half minus 10 to the half. Now, if you rewrite this, that's a square root of 160 minus the square root of 10. I can't do that, can I?
No, sir.
I gotta get them within the same base, right?
Yeah.
So, is there a perfect square hiding in the 160?
Can't be
16. So, how would you simplify the square root of 160? What would you get?
40.
This is 4 root 10 minus, what's the value in front of the radical here?
1.
Minus 1 root 10 gives you?
3 root 10.
Awesome.
You've done that problem in the past, you just didn't do it in terms of a fractional exponent. Am I right? Am I right?
That one was easy. But all the rest, not so much.
All right.
I like the variable.
Variable ones are going to be a little bit cleaner because you guys are accustomed to it. Okay? 51 should be a piece of cake. I don't think that'd be an issue at all. Yep. Now the bottom one, that's where things get interesting. I need to find perfect. It's 5 minus 7. I want to find perfect cube. So I'm looking at this. I have one of them that ends in a 5, which means I might want to see if I can divide that by 5.
125 times 3 3.
So isn't this the cube root of 125 times the cube root of 5?
Yes. 3.
3. Excuse me. Isn't that right?
Yeah.
Isn't that the other one? The cube root of 27 times the cube root of 3?
Yeah.
What do you think about that?
I'm simplifying the roots to get the same base. What's the cube root of 125?
5.
What's the cube root of 27?
3.
What's 5 plus 3?
8.
Oh, I
Wait.
Is it gonna be 2 cube root?
5, and then
Aren't there 3? Never mind.
Get rid of cube root 3, what?
The cube root of 125 is 5.
yeah.
Yeah.
So it's 5 cube root 3 plus 3 cube root 3. 5 and 3 gives us the 8. Does that make sense, Anna? I once again, I just vocalized it. I just didn't write it down. I'm just never lazy about writing. Yes, ma'am.
Just starting to do 32 and I still don't understand.
Let me finish these through, okay? And then lastly, obviously I can't do anything because they're different roots. But if you look at it, the 11, the 4th root of 11, I'm pretty sure I'm done on that one. But if I divide 176 by 11, what do you get?
16.
It's 16. What's the 4th root of 16?
2.
So this becomes 2 times the 4th root of 16 times the 4th root of 11 plus 5 4th root of 11.
Where did that come from? Which number?
So it's 9.
52, or 55, sorry.
Yep. Sometimes they give you a value underneath the radical that won't be able to be simplified. Just like you did with square roots, you would just see, all right, what's the other number divided by 11? 16. 16 is the perfect 4th root. Yes, ma'am?
Where did you get the second two?
What's that?
Where did you get the second two?
What's the 4th root of 16? What are 4 numbers that are exactly the same multiplied together to get 16?
Oh, 2.
4 plus 5 is 9. Okay? Now, the last bit of this section then gets into the working with the variables looking at this. To be honest with you, you're going to be better at variables than you are with numbers because you're used to them. You're used to simplifying exponent rules with variables. You weren't used to being able to sit through and sift through the ideas of simplifying them numerically. All right? What I want you guys to do, we did an example the other day of division, right?
Yeah.
I think we did. Real fast, let's just look at this one.
I forget it.
When I want to take the 4th root of that monomial, if you will, it's a really nice, easy way to simplify stuff. What I do is I start with, can I do the 4th root of 10?
No.
No. So I can't simplify that. There's no perfect fourths that go into 10, right?
Yeah.
So I know that my answer is going to have the 4th root. The 10's got to stay in there. 4 goes into 5 how many times?
1.
What many are left over?
1. Oh.
Because here's what I want you to think about. Hold on. Let me finish this out. 4 goes into 8 how many times? Any left over?
No.
4 goes into 10 how many times?
2.
How many are left over?
2.
Because here's what's happening. And Austin, I think you missed out on this one the other day. This is the same thing as saying 10 to the 4th, x to the 5th to the 4th, y to the 8th to the 4th, z to the 10 to the 4th, which means it's 5 over 4, which gives you 1 and a 4th. This is 2. Gives you 2. This is 2 and 2/4.
No, it's 10 over 4 because no mixed fraction.
Okay? That's what we were doing on that one. So it's just faster to verbally say it than it is to rewrite out.
Okay.
Okay? We did one of them. I think that's all we ever did on that. Now, let's see here. Here's what I want you guys to do. I want you to do, what page is that? 412? It's the same stuff. I want you to go 56 to 90. I want you to do the evens. No, because I did a lot of them, so that we've got a chance to look at them and make sure you got them right.
Can I just add them to?
That's fine. If you want to do that. I would, let's see here. We got next section is what? Inverse? Yeah, that's fine. I need to do the inverse before we quiz or no? Yeah, we'll do inverses don't take long to go through, so we'll probably want to quizzing midweek. We'll probably do it Tuesday, just so you guys know. All right?
What are we doing?
Yes, ma'am. I don't know. Math? Let me do this real fast here, guys. On 29. On 29, it's asking me to do this, right? It's power to power. Power to power. Okay. Which means you have to multiply your exponents together, correct?
Yes.
What's 2 times negative 1/2?
Negative
Negative 1.
Negative 1.
Negative 1. Negative 2, it's negative. Okay.
Okay, well, I'm just going through all this stuff.
Is he happy?
No.
Is he happy?
No.
8/5.
Wait, why can't you cancel out the squares?
What? Oh. You can't do that.
Can't do that in exponents. Does that make sense? Break it down into something that's the most simplistic way of looking at it. Use the properties of going power to power before you try to mess anything up. Yes, ma'am.
Do you have like negative that's not the same like that? Can you just
That's the same. Yeah. The other way of doing that.
Wow.
That's what you're saying? Same thing. Means the same thing. Okay.